Hello everyone, welcome to a new series on my channel. This video is the introduction to the design, prototype, testing, and construction of a new monoblock tube amp with some interesting twists. I plan on keeping these videos to a limit of 20 minutes, breaking the series up into chapters which focus on individual aspects of the design. As an introduction, let's go through a bit of the background as to why I started this project. I have a stereo tube amp that I built from a kit a few years ago. I did some improvements to the amp, but it's only a 12-watt stereo unit running single-ended EL34B output tubes. The amp sounds great, but it doesn't have a lot of low-frequency performance. As an addition to the system, I decided to try an experiment and see if I could make a tube-based monoblock channel or single channel amp as a center channel. Some additional ideas I added was to try and make the output stage using Quad6AQ5 output tubes in a push-pull configuration. And to make it more interesting, the design will use a quad output configuration. That is to say, 2 tubes per side on the push-pull arrangement. I also wanted to add an active low-pass filter to the front end in the form of a boost cut circuit and then a passive low-pass. The amp only needs to amplify a left and right summed output of the lower frequencies, tapering off at around 400 Hz, so it would also have a low-pass filter in the same circuit, which I mentioned previously. To drive the quad output stage, I wanted to experiment in a tube-based phase inverter circuit, using a design that boasts a low THD, that is to say, total harmonic distortion, or noise factor. Essentially a phase inverter that has very good linear characteristics. The amp should be in a small, compact form factor so that it can be situated alongside the existing amp on the stereo console. In order to try and get a compact wiring layout, I'm going to design part of the amp using a more modern components and built onto a PC board. This makes the amp into what I'm calling a hybrid design, that is to say, a bit of old and a bit of new. So laid out on the table here are some of the components that I've gathered to date. The chassis is a 10 by 6 by 2 box, metal from Hammond. Part number is 1441116BK3. This is going to form the chassis or the body of the amp, and it's going to face this way with the transformers on the top here and the tubes in the front, and front controls. As I said, the chassis is metal, as it's more capable of withstanding flexing from the heavy transformers mounted to the top than an aluminum enclosure would. This does mean, though, that drilling holes will be a tougher job. Speaking of holes, one part of the build that I want to accomplish is a clean design on the top surface with a minimal amount of hardware showing. The stereo amp that I have right now uses a subplate for mounting the tubes, and I'm going to try a similar technique on this amp. I said that there is to be a minimum of hardware on the top surface, but this will mean that more holes and hardware will be used on the sides of the chassis. This is okay, as the amp will be completed by wrapping the sides in a 3/16 to 1/4 inch thick wood siding, forming a box open to the top and bottom. The wood box will hide the hardware on the chassis sides. The power transformer I'm using is a Hammond 370HX. Get it in the shot there. It's a fairly hefty beast. It can output 550 volts center tapped at up to 200 milliamps. It gives me a lot of headroom in terms of deliverable high voltage power. It's certainly a bit overkill for 6AQ5 tubes though. I'm planning on using more modern silicon rectifiers, but I will still use a choke to form a pi filter for smoothing the 120 Hz ripple out of the DC voltage. The choke I chose is the Hammond 157R. It's rated at 2 Henrys, 200 milliamps DC, which is compatible with the transformer that I have already chosen as well. It's a good matchup. In addition, the choke is small enough that it can actually fit on the side of the chassis. So its height here is less than 2 inches. So I can mount it on the side, on the inside. I'm going to have to do that because space is a little bit tight in the chassis. As the amp is a hybrid design, it will need lower voltages to supply the preamp and the filter. I plan on having another transformer in the chassis that can supply positive and negative regulated DC voltages around 12 to 15 volts DC. This too would also have to be located on the chassis wall due to tight spaces. So to illustrate the mounting of the devices, just to reiterate, the transformer, the choke will be inside the box like that. The other DC transformer for the low voltage power supply will be on this side of the box. The tubes will be up front, and on the top we'll have the power transformer and the output transformer, like so. Roughly there. Let's go to the output transformer. It's again a Hammond 20 watt 1620 transformer. So its primary impedance is 6,600 ohms center tapped, and it has screen taps at 40% on the primary. Of course, it's push-pull, and it has taps on the output, the secondary, for 4, 8, and 16 ohms. Again, 20 watts is a bit overkill for these small tubes here, but the idea here is that a more hefty transformer like this should be able to better replicate and pump out the low frequency spectrum of the audio, which is the whole purpose of this amp in the first place. The subplate I mentioned earlier is a metal plate that has all of the tube sockets mounted in the desired layout. The plate would sit inside of the chassis. If the transformers are here, the plate would be here in this location, and it would be situated about a 1/4 inch below the surface of the top. The tubes would be poking through larger holes in the top of the chassis. Like that. And this gives it a clean design because there's not a lot of hardware for the sockets, or, for example. They're not actually mounted on the chassis top. Rather, they're mounted on the subplate, which gives a cleaner look because you're not seeing the hardware for the sockets on the surface. And the tubes just poke up through the top. There's a gap around the tube that allows hot air flow to come up past the tube and cool it. It also sucks in cold air from underneath the chassis, cooling all of the internal components as well. So I get a kind of a heat pump effect or an air pump effect by using this. The tubes I've chosen are new old stock. I did measurements on them and they're all really close to a standard rating. The maximum that these tubes can be in theory is 4100 in terms of their GM, and these are very close. This one's 4100, this one's 4000, 4050 I believe, and 4050. So I'm thinking that using these four, they should complement each other and I should have a fairly balanced current flow through the tubes. The power connector is going to be one of these modules. I like these because they're very nice. There's a fuse in here, and I put in a, I believe it's a 1.5 amp slow blow. If I need a slightly larger fuse, I can substitute one in there. It's a standard IEC power connector with a built-in power switch, and it comes out very nicely here, and it's easy to wire up. As I said, it's all in one unit. It would go into the chassis right about here, and it would actually be embedded a little bit inside of the wooden box surrounding the chassis to neaten it up a little bit. But there's going to be a fairly large hole in the box, of course, to accommodate this going into the chassis. The phase inverter, I'm going to use a 12AU7. I did some preliminary testing of this, and this doesn't have a lot of gain, but it is a fairly good match in terms of where I want to sit on the current flow going through the tube when it's not operating. That is to say, the quiescent current. I think I've set that to 5 milliamps for both left and right triodes. So per triode, the current flow is 2.5 amps. This becomes important, as we'll see in a later episode. The design of the triode, or the design of the phase inverter, heavily relies on balanced current flows inside of the two triodes, and that's how it works. So it's not the standard cathode plate style of phase inverter. This one's a little bit more sophisticated. Knobs for the project, I'm probably going to use something like this. I picked these up from Antique Electronics Supply. It has volume and tone on it, so it kind of is already labeled. I don't have to worry about labeling it. And I'm kind of making up in my mind right now about whether to use these volume knobs or go with something else, like maybe these. These are a Marshall amp knobs for a tube guitar amp. And they look quite stylish. I like the gold trim on them. However, they're not labeled or anything like that, but they do have markings for their location. So we'll see, we can try out different ones. It's pretty easy to interchange these. I'm using a standard 18 spline push-on potentiometer for these, so they're interchangeable. I just did a quick draw up of the block diagram for the tube amp. Just to go through the major component blocks and see where we'll be designing components or parts in. So the first part would be the power supply. We have a high voltage and low voltage section, and that's generating all the voltages needed for the two major circuit or voltage domains. So we generate a B plus and a B plus plus on the high voltage, and the low voltage generates regulated plus and minus 12 volts or 15 volts DC. The front end, the audio front end, will be taking in line voltages for left and right channel, and immediately also creating a pass-through connection with a second RCA port for each channel. This allows the bass amp to be placed in between the audio source and the stereo amplifier that's already in existence. This will intercept the line voltages and will combine them together and create the audio driver output for the tube, or the high voltage section of the stereo. Both left and right channel are sent through a volume control. This gives the 50K of impedance to the line inputs. Those are then summed together and buffered before they go into an active boost cut filter, and this boosts and cut low frequency aspect of the frequency domain of the signal. That then goes through a passive low pass filter, which just gets rid of everything above, say, 400 hertz or so. That then finally goes into a driver, and that buffers the signal to go to the phase inverter. In the high voltage part of the tube circuit, or the circuit, we have all the tubes. So we have a 12AU7 running as a phase inverter, giving us 0 and 180 degree phased audio from the driver. In the output section, we have a push-pull setup with 2 tubes per side, giving a total of 4 Quad6AQ5 tubes. And then that goes to the output transformer, and then driving an 8 ohm load to the speaker. Previously, I mentioned that I'd be using impedance or reflection properties of the transformer. That was kind of an error. I don't think I need to worry about changing the tap to create a new 8 ohm tap to change the turns winding ratio to get a different impedance on the primary. And I'm just going to go through that as an explanation of why I think I can use the transformer as is. I'm going to bring in the datasheet, the RCA datasheet for the 6AQ5A tube. This is a copy that actually has more information than the normal RCA page, which tends to not talk about class AB or push-pull amplifier configuration. If we look at recommended parameters for a class AB1, that is a push-pull, we can say that the maximum plate voltage is limited to 250 volts. In the operation, there's saying a recommended effective load resistance plate to plate is 10K or 10,000 ohms. Our transformer that we're using is 6,600 ohms. If I was just using 2 tubes and a push-pull setup, the primary impedance, in this case marked as ZP, would have to be around 10,000 ohms for this to be an effective coupling impedance matching between the tubes and the transformer. In our case, though, we're using 2 tubes per side, effectively cutting the impedance in half. So we would only need 5,000 ohms on a dual tube setup, because these impedances here are in parallel, and any impedance in parallel is divided or averaged out, I guess you could say. It's the closest approximation. Resistors in parallel have a lower common impedance than they do separately. So I'm going to probably just be able to leave the 8 ohm as it is, use the 8 ohm as the 8 ohm, and that leaves me with a primary impedance plate to plate of 6,600 ohms, which is fairly close to 5,000 ohms that would be in here. We'll see how it works, and we'll do some THD measurements of the amp once we get down to that stage in the design. So that's all I have for this video. Next up will be coverage of the schematic that I came up with, some discussions on design decisions, and I think we'll also look into some of the mechanical designs that I am going to fabricate if there's enough time at the end of the video. I imagine that going through the schematic is going to be fairly involved. I hope this series will be of some interest to people. Tune in to see if this becomes a successful design or a lemon. We'll all know more as we get further into the prototyping of the design blocks. Cheers for now.